We are moving into our unit on logarithms, and soon you will realize that a logarithm is really just an exponent. And so we're going to quickly recap some stuff we know about exponents and touch upon real exponents. We've talked about rational exponents before, but before we talk about that, let's recap some things about exponential functions that will become important when we talk about logarithms. So some f of x, which remember is the same thing as y, equals b to the x, is an exponential function if b, first off, is greater than 0 and not equal to 1. And those zeros and those ones are important for logarithms. Exponential functions actually grow faster than polynomial functions. So if you have any polynomial of any degree, it's going to be outpaced by an exponential function. And remember that the domains of these exponential functions are all real numbers, which means, of course, non-integer exponents exist, and then non-rational exponents exist, which we really haven't touched on, but we will in today's lesson. So a quick reminder on rational exponents. Remember, the numerator was the power and the denominator was the index of a root. So we made roots a part of exponents as well. And whether or not I want to take the root before raising to a power or taking the power before taking the root depends on the situation I have. So in the case of 64 to the 2/3 power, I don't want to square 64 because that's horrible. I would much rather take the cube root of 64 and then square it. And the cube root of 64 is 4, so 4 squared is 16. Now what we haven't really talked about is how to deal with irrational exponents. And it's really no different than dealing with rational exponents. The exponent properties all still apply. So if I see 5 to the square root of 3 power divided by 5 to the negative square root of 3 power, you can use the division property of exponents that say you subtract this bottom exponent, and you can combine those into 5 to the 2 square roots of 3 power. And so that's simplified. I can't do anything to that except find a decimal approximation of it. And so if I look at this example down here, which is slightly more complicated, 25 pi times 5 to the 3 minus 2 pi power, it seems like, oh, I can't simplify that because the bases are different. But you're in Algebra 2, and the expectation is that you can think in a little more sophisticated fashion and realize, oh, hey, check it out. 25 is really just 5 squared, and then apply the power rule to that to get something that you can indeed simplify further. So then I get 5 to the 2 pi times 5 to the 3 minus 2 pi, and then the product rule says to add the exponents, and so I end up with just 5 to the 3rd power, or 125. So irrational exponents aren't a big deal. Now, when we were solving equations, I really didn't touch upon this technique very much, but you could have just as easily raised both sides of this equation to a reciprocal power, say the 2/3 power, and solved for y. I don't know if you realize that. So I can just use the power rule. If I raise this side to the 2/3 power, I just end up with y minus 2. And if I raise 8 to the 2/3 power, I get cube root of 8 squared, which is 2 squared, or 4. And then I have a very simple linear equation, y minus 2 equals 4, and I get y equals 6, which I can then just plug in to make sure that it's not extraneous and does indeed work, and it does. So now let's look at this second example. And if you think about what this example really is, it's really an equation that looks like that. And if I rewrite it as an exponent, I actually find it's easier to deal with because I can simply divide by 5 and get x to the negative 1/2 equals 4, and then raise both sides to the reciprocal exponent, and I get x equals 1/16, and I can go back and check to make sure that works. One thing we really didn't touch on at all when we were solving is how to solve equations with variables as the exponents, because you needed some way to get the variable out of the exponent, which means you need some way to reverse exponentiation. But you don't always have to do that. Sometimes the equations are written in such a way that if you just use your exponent properties, you can manipulate the equation to avoid having to undo the exponents altogether. And so the technique for that is to get the same base on both sides, because we have this property of exponents called the uniqueness property that says if I have some base to some exponent equaling some base, the same base to another exponent, then those two exponents have to be equal. And so if I can get the square root of 125 to be base 5, then I can just compare exponents. So 125 is 5 cubed, right? So I have the square root of 5 cubed, which I know square roots are really half powers. So I have 5 to the 3 halves power is the same thing as the square root of 125, and 5 to the x equals 5 to the 3 halves, and by the uniqueness property, I know that x has to equal 3 halves. So if you can figure out a way to get the bases the same, you don't have to worry about having an inverse function for exponents. And this one here, I can do the same thing. 27 is really 3 cubed raised to the 2x minus 1 power equals 3. I can use my power rule and have 3 to the 6x minus 3 equals 3 to the first power. And so then I know my exponents have to be equal, and then I can just solve, and I get x equals 2/3. And sometimes you have to be a little creative to find the appropriate base. Like I could write 8 as a base of 4, or 4 as a base of 8, or I can just write them both as base 2. So I can do 2 to the 1 minus x power equals 2 to the third power. And if you notice that you can do this, this is actually an easy way to solve the exponentials, but you have to be able to find the same base. Now, of course, that's not always the case. You can't always find the same base, and so we need something else for that, and that something is called a logarithm, which we'll talk about in the next video.